Namaskar and welcome to the second lecture of bulk characterization, wherein we would look into the further particle properties which are important not only from the formulation point of view but also from the processing point of view, because the particle properties has an impact on the surface area, then its flowability, how the particles are packed, what sort of void spaces are there, how much airy the particle bed is, whether it is flowable or not, because all these properties are required when we are going specifically for the solid dosage form manufacturing and development. So these properties need to be understood with respect to each of the material prior hand only, so that they can either be used as such if it is in favor of the characteristics expected from the dosage form, or they can be altered so that they can suit the requirements of the dosage form type. So we will look into these properties in this specific lecture. Now in this we look into the micromeritic properties, that is particle size and distribution, volume, density, porosity, hygroscopicity, and then finally the takeaway. Now micromeritics is the science and technology which deals with the small particle properties. The micromeritics is thus the science which deals with the small particle properties. There are two types of properties, one is the fundamental, the other is the derived property. The fundamental property is the property which is inherently because of the particle characteristics, that is what sizes it exhibits, what are the distribution, what is the distribution, that means what is the difference between the minimum and maximum size of the particles, what are the number of particles in each of these in this size range, is it not that there are clumps or clusters of particle sizes. So that we will look. Surface area, as we have seen a lot of times, that surface area is directly dependent on the size. So smaller is the particle size, larger is the surface area, because it is the surface which is interacting during solubilization, during absorption. So surface area is important. Then the particle volume, what is the volume exhibited by the particle, as well as the particle shape, that is how much regular or irregular the shape is, whether it is oblong, circular, globular, flaky, in the form of needles. So what is the shape, because each of these shape has an impact on one or the other product characteristics. For example, globular particles flow easily, however irregularly shaped particles get interlocked and either do not flow or they flow in clumps. They'll form a big aggregate and they are very resistant to flow. So the particle shape has a very crucial role, especially when we need to make the particles flow, especially when we are talking of the capsule filling or when we are talking of the tableting operations, wherein the granules and the particles need to flow. Then based on the fundamental properties, there are a few derived properties. These derived properties are the density. Density means what is the volume and how is the volume of the particle derived. That is whether it is the true volume, that we will see. So depending upon the volume, the density will change. Then what is the porosity? How are the particles arranged? So if there are all similar size particles, they will have a different arrangement. If there are larger and smaller particles, the arrangement is going to change. Now based on this, how the flow of the material is going to change, and based again on how the arrangement of particles is there, the bulkiness would be different of the particles. So if there are very large particles, they will be bulky. If there are large intervoid or void space, it would be a dilatant as well as a bulky powder. So that is what we mean by the bulk characteristics. So bulk characteristic is as we are dealing with not one particle, we are dealing with some kgs of material. So this material thus becomes bulk, and how it is going to behave when we are using them in bulk. So maybe a small number of particles when they are there, they behave differently because they are in agreement with their shape they might be very similar, their shape and their sizes might be similar, and hence their flow as well as arrangement might be same. But when we are talking of tons or we are talking of kgs, the range of the particle size, the manner which they are arranged, the surface properties generally tends to vary. So characterization of these properties for the bulk material becomes important, specifically from the manufacturing point of view when we are going for large scale production of these formulations. Now, particle size, coming to the first property, that is the particle size and the particle size distribution. Particle size is quoted as the diameter of the sphere that has the same weight when we go for weight based diameter, or same volume when we go for volume based diameter, or same surface area, area based diameter, same drag coefficient or sedimentation velocity when we go for hydrodynamic or aerodynamic based diameter to the given particle in consideration. Now, once the particle size is got, it needs to be distributed. That means we need to know that since we are dealing with bulk material, so we need to know what is the range in which the particles are there. So if the particle size exhibit in one specific range, it is called as a monodispersed. And if it is having different size of particles, that is there are ranges of particles, it becomes polydispersed. So polydispersed particle will have more than one range. Maybe for example you have from 10 to 20 micrometer particles are there, so you will get a number of particles. Then maybe you have extremes, that is 100 to 200 micrometer. Then you can, on the lower side, you have 0.1 to 0.5 micrometer particles, that is nanometer size range, 100 to 200 nanometer. So when there is a there are range of the particle sizes, it is called as a polydispersed. So the dispersity or the distribution of particles increases over particular measurable size range. Now, in the figure 1, we can see a size frequency distribution of particles, which is called as a normal or a Gaussian distribution. Here the number of particles, the frequency, that is the number of particles in a specific size range, are plotted and we get a distribution. So it should be more or less superimposable, that is, if when we draw a line from the mid, which is generally the average of the particles, and then it should the one half of it should be superimposable on the other half of the particles. There are various techniques of determining the particle size. So we can use microscopy. Microscope used will depend on the will vary with the kind of size range being considered. So if these are cruder particles, we can go for light microscopy. When we want higher resolution, specifically in this lower size range, that is micro or nano, then we go to electron microscope, which could be a transmission electron microscope or a scanning electron microscope. Then next is by sieving. So this is weight based measurement of the sizes. So a series of sieves, as we can see here in figure 2, are arranged from the crudest to the finest sieve, which being at the bottom, and the weight of sample retained on each of the sieve is measured, and then it is correlated with the size of the particles. Now then there is sedimentation. Sedimentation gives a theoretical description of the motion of the falling object under the influence of gravity. So how particles sediment, based on that the size can be measured. So de-Stokes is a method wherein the fluid is taken of known viscosity, so and then the rate at which it is falling is noted. G is known, that is a gravitational constant, and the difference in the density of the particle and the medium, which is also known, is put in the specific formula, and the diameter of the particle can be measured. So this is based on the rate of sedimentation of the particles. Then there is Coulter-Counter method of determining the size of particles. So in a suspension, specifically dilute suspensions are taken and they are made to pass through an orifice, and as they pass, the resistance will change. So there are electrodes on both the sides, and as they pass, there is a change in resistance which is noted, and this is then calculated in terms of the size. So basically what happens is, when the particle passes, it will displace a specific volume of electrolyte which is equivalent to its own volume, and this causes a change in the electrical resistance, and which is then reflected in terms of its size. Then there is a surface method which is conventionally used. We adsorb the surface of the powder with air or liquid in a monomolecular layer, and then this adsorbed volume helps us in determining the mean of the powder's particle size. Then there is dynamic light scattering technique, in which the particles are bombarded with the light. They can deflect the light or absorb the light. So larger particles generally diffract, and smaller particles with wavelength range of the particles, they tend to scatter the light. That is why generally dilute suspensions are used, so that single particles can be bombarded, they encounter the light, and the size can be easily determined. So if it's a non-dilute suspension, maybe 2 or 3 smaller particles can be perceived as a larger particle, and error in the size measurement can occur. So dilute suspensions are used in this technique. Then there is cascade impaction, which is generally used for respirable particles which are to be fluidized and then inhaled. So there is instrument which is called as cascade impactor, and from that the powder is fluidized, and based on the size they are retained on different cascades. So the heaviest particle settle first, and the largest particle flow to the peak, and then they are retained at the top. So this is how the sizing can be done, and this is generally used for determination of the aerodynamic diameter. Now the properties which are related with the size are the area. So as size is required for dissolution, absorption, solubility, and hence the bioavailability of the having good bioavailability of the drug. So by decreasing the particle size, we can increase the area, and hence it is expected that the solubility can be increased. So Noise-Whitney equation is mentioned here, wherein the rate of dissolution can be seen, that how for different surface area the rate of dissolution can vary, wherein the solubility of the compound at a specific time, as well as the saturation solubility of the compound is mentioned, and the thickness of the dissolution layer. So Noise-Whitney equation though is generally used in the dissolution, but its underlying principle is basically the area, surface area of the particles. Table 5 mentions various techniques which are generally used for with the size range for determination of the particles. Now porosity is how the material is arranged. Now density and porosity are interrelated and are influenced by particle size distribution, shape, surface area, and arrangement of molecules. As we all know, density is the mass per unit volume. When we are determining the density, mass is constant, but the volume which is there varies because of the different types of void spaces in the material. So hence the density will vary. Now when we talk of a bulk powder, there are generally 3 types of void spaces in the material. One is the open intraparticulate void spaces, which are there within the particle and are open to external environment. Then there are closed intraparticulate void spaces, which are also present in the particle, but they are not open to the environment. Then there are interparticulate void spaces, which are present between the 2 individual particles. Now depending upon these 3, the volume of the material will change, and hence the density of the material will change. There are 3 types of volume. One is the bulk volume, true volume, and granular volume. In the bulk volume, the total volume occupied by the mass, including the voids, both intra and interparticulate voids, is taken. In the true volume, the total volume of the solid, excluding all spaces greater than the molecular dimensions, that is the intra and interparticulate space, void spaces are excluded. So it is just the volume of the particles. Then there is granular volume, which is the cumulative volume of the particles including the intraparticulate void spaces, both closed and open, but it does not include the interparticulate void spaces. So based on that we get three types of volume. Porosity is basically measured by determining the volume of the void spaces, which is calculated as the difference between the bulk volume and the true volume, and porosity is basically the ratio of the void space volume to the bulk volume, and percentage porosity is the ratio of the void volume upon the bulk volume into 100. So hence as the volume changes, the density will automatically change, as it is density is mass per unit volume. So once you consider the true volume, you will have a true density. You consider the granular volume, you will have a granular density. When you consider the bulk volume, you can calculate the bulk density of the material. And depending upon the size as well as the packing, the bulkiness of the material will change. So generally with increase in size, the bulkiness changes, and also it has an impact on the packing of the material. Packing means how the material is placed in a specific dosage form. Now as we were discussing that the material particles also impact the flow property. So and how much you can compress it. So that also we can calculate based on the density as well as the volume of the material. So percentage compressibility is how much the decrease in volume occurs when you apply the pressure. So for calculation of percent compressibility, we take the difference of the tap density and bulk density, and it is then divided by the tap density. So we get the compressibility and hence the percentage compressibility. So this is the Carr's index, which is the percentage compressibility. So we can see here that it comes in ranges. So based on the percentage compressibility, you can determine what the flow pattern of the material is going to be like. So if it is between 5 to 15, it's an excellent flow, 12 to 16 good, and likewise 18 to 21 fair passable. That means fair passable means it has an optimal flowability. It can pass, but there is a probability of posing few challenges. Then 23 to 28 poor, 28 to 35 poor fluid, that is it has a cohesive powder. That is, cohesive means the powders are very sticky or have good interparticle bonding. 35 to 38 very poor, the fluid is still cohesive, and more than 40 extremely poor and cohesive powder. Now another kind of parameter, that is the Hausner's ratio, also helps in determining the compressibility as well as the uniformity of dose and flow property of the material. So Hausner's ratio is tap density upon the bulk density. So if the Hausner's ratio is bit less than 1.25, it has good flow, 1.25 to 1.5 moderate, and more than 1.5 it's poor flow. Now what do we do with these ratios, or where do we apply it? Now once you have this ratio for the parent material, you can modify it using certain additives or certain excipients, or you can change the particle size, or you can change the processing parameters so that the flow property can be changed. As we have seen that these flow properties as well as compressibility are all guided by the particle size and its arrangement. So we can either use fillers, or we can use excipients like glidants or lubricants, so that the flow property of the material can be enhanced. If it's a coarser particle, we can go for spray drying and we can change, we can get a smoother morphology so that it flows properly. So the idea here is that once you get these values for a specific material, in which line it needs to be proceeded, so that how it needs to be processed or what excipients need to be added, so that it can be brought into a range which is good. So a poor flow material can be brought into a passable or a good flow range by adding the additives or by changing the process of its size reduction, like we can go from simple milling to spray drying, which helps in getting us globular particles. So the processing as well as the type of excipients which can be used can be determined, and they can facilitate in the scaling up as well as in the formulation development process. So coming in line with this, as we were talking of the another parameter, that is flow. So angle of repose is again a parameter which is used for determining the flow property. So theta is the angle of repose, and we find out tan theta, which is equal to h by r. We will see how it is calculated. So there are three techniques by which it can be calculated, that is a funnel method, rotating cylinder method, and tilted box method. In the table 9 we can see various ranges of the angle of repose, that is less than 25 it's excellent, 25 to 30 good, the material is non-cohesive, 30 to 40 cohesive, and more than 40 it has very poor flow and it's a very cohesive material. So the three techniques which are used. So in the figure A, it is a funnel method. What is done is a funnel which is fixed at placed at a fixed height, and it's placed on a graph paper, and a fixed amount of material 5 grams or 10 grams is made to flow from the funnel, and when it falls through the funnel it creates a heap, triangular heap. So the diameter of the heap and the height of the heap is noted, and from the diameter the radius is taken, and from the height h is taken, and theta value is calculated. So this is a static method of determination of angle of repose. Then there is a kinetic or dynamic method for determination of angle of repose. In the dynamic method we use the rotating cylinder method. So a hollow cylinder is half filled with the material, and it's one side of the cylinder is sealed with transparent glass plate, and the wall is lined with the sandpaper, so that the material flows, there are no slips in the material. So when the material is rotated, it creates a horizontal axis. So as we can see in the figure B, the material while rotating and it comes to a standstill, it creates a after it has come upon rotation, when it comes to stabilization, it creates an angle. So this angle helps in determining, this is the angle of repose, this theta is taken into consideration. Then there is the tilting box method, wherein a rectangle box, which is again lined with the sandpaper, is filled with the powder and tilted till its contents begin to slide, and the maximum angle that it makes with the plane of powder is the angle of repose. Now there will obviously be a difference in the flow of the slipping pattern of the coarse and the smooth particles, as well as what is the size range. So if it is non-cohesive powder, smoothly granulated, and shape is smooth, the particle size in a specific range, that is monodisperse, you will get a uniform arrangement of the particles. However, as against this, if the particles are rough, they are of polydisperse range, very small fines, then the movement of the material will be different, and you will get a different pattern of the sliding of the material, and its theta value will change. So the nature of the material determines how it is going to, nature with respect to its size, shape, cohesiveness, adhesiveness will determine how it is going to flow. The objective is that it should be reasonable, so that we can use it in our further manufacturing as well as scale up operations. Now coming to another property which is related to the moisture absorbing or moisture releasing property of the material. So the first of it is the hygroscopicity. That is a tendency or ability of a material to absorb moisture from the atmosphere, and it is in equilibrium with the atmosphere. Then if the material further absorbs moisture and liquefies, so then it is classified as a diliquescent material, or it can, upon absorbing, it can form a solution itself, completely solubilize. So these materials are diliquescent materials. Then there are efflorescent materials which have a tendency to lose moisture to the atmosphere and they become dry. So the materials can be classified based on the amount of moisture gaining, which is calculated in terms of increase in their weight, temperature of 25 degrees and 80% RH. So the European Pharmacopoeia Technical Guide has given these classifications. For a slightly hygroscopic material, when it is kept at this temperature and humidity, that is 25 degree and 80% RH, if the increase in weight is more than 0.2% weight by weight and less than 2% weight by weight, it is slightly hygroscopic. If the increase in weight is more than 0.2% weight by weight and less than 15% weight by weight, it is hygroscopic. Very hygroscopic if the increase in weight is more than 15% weight by weight, that is, it is absorbing moisture highly. And diliquescent materials are, if an absorption they form a solution or they liquefy, it is a diliquescent material. So we saw that the material properties are determined and they change depending upon the kind of environment they are having, as well as what inherent properties are there. So these fundamental properties as well as derived properties are there and they are required to be studied, so that the objective of all these studies is in the end formulation of a bioavailable and a stable dosage form. So hence we need to see the backhand properties. So size, to summarize, plays an important role in packing, flow properties, which is further determined by porosity and is reflected in terms of bulkiness and surface area. And the moisture absorbing or releasing property is important to select the right kind of material, so that it can be processed properly, or it may not be used at all, or it can, an excipient can be used which can minimize its tendency to absorb moisture. So if it's a hygroscopic material, we may not be using it, may not be processing it in a dry condition. We will definitely prefer to formulate it as a liquid, so that whatsoever it is always there in a moist condition, moisture is there and it is not going to absorb moisture. However, if we formulate it as at a solid form, solid dosage form, there is a high likeliness that it may absorb moisture and get degraded. So this identification of the moisture behavior of the material to absorb or deabsorb moisture and the size characteristics are very, very instrumental in determining the quality and stability of the dosage form. Thank you very much for your patient hearing.